when solving maximum minimum problems, I guess the key process, we get given a scenario of some kind. It's really a form of modelling, and we have to try and find some equations. Try to get those equations in terms of one variable, normally x, or it could be r for the radius, or dependent, whatever we're measuring, and then differentiate to get a maximum or minimum value. So it really is a case of treating each question as we go. So here we've got a cylindrical can. So it doesn't hurt if we actually do a diagram. Our can has a radius and our can has a height. All right, so closed at both ends. Okay, so it's got a top and a bottom. The surface area is 100 centimeters squared. So the surface area is equal to 100. Find correct to two decimal places the greatest volume it can have if the radius of the canister can be at most 2 centimeters. Okay, it looks like two different questions there. All right, so first things first, find the greatest volume of the can. Okay, so we know the volume of a cylinder, it's on our formula sheet, is pi r squared h. All right, so we want to find the maximum volume, so that implies working the derivative out with the derivative of v, but we've got two variables there, r and h, so we need some more information, okay? The other information comes from that surface area. So what is the surface area of a cylinder? Again, I reckon it's on our formula sheet, but we've got two ends, or two circles, so the surface area is equal to 2 pi r squared, and if you open up the cylinder, we've also got the wrap around the outside here, okay? And so the piece of paper, or the piece of metal that wraps around, like an A4 piece and wraps around and forms a cylinder, the height of it is actually the circumference of a circle, which is 2 pi r, and the width of it is actually h. So my formula, 2 pi r h. So that's the formula for the surface area. So let's rearrange that to get what h is equal to, because we've now got an equation here. Okay, so there's our second equation. So if I just come across a bit, 100, let's minus 2 pi r squared is equal to 2 pi r h. So let's divide by 2 pi r. So we'll get h is equal to, I could do 2 into both of those, so I will. So I'll get 50 minus pi r squared over pi r is equal to h. Okay, so I can put that into my volume equation. Volume is equal to pi times r squared times the h, which is 50 minus pi r squared over pi r. So pi cancels with pi, that r cancels with that r squared, so I get left with volume is equal to, there's an r at the front, 50r minus pi r cubed. So there's the rule for the volume of my cylinder. To find the maximum volume, I need to find the derivative equal to 0. So in this case, dv dr is equal to 50 minus 3 pi r squared. So let's come down this way a bit. So the maximum occurs when that's equal to 0. So I get 3 pi r squared is equal to 50. R squared equals 50 over 3 pi. So r is equal to the square root of 50 on 3 pi. Positive only because the radius is obviously positive. So that's where the radius, that's what gives me a maximum volume. So if I put that into my volume equation, volume is equal to 50 times the square root of 50 over 3 pi minus pi times root 50 on 3 pi cubed, and I'm going to use a CAS and get an answer for that, which I won't do just now, to be honest, because I don't have a CAS handy. All right, so there's my maximum volume. Now this radius value, okay, R, I'm going to have to work that out, so just give me a minute. Look at that radius there, so I'll put in red. that radius is equal to 2.39 centimeters. Okay, so the maximum occurs at 2.39 centimeters. Now, the second part of the question here says the maximum radius can only be 2 centimeters. So since r has to be less than or equal to 2, the maximum is at r equal to 2. And if I put r equal to 2 into my volume equation, I get 50 times 2 minus pi times 2 cubed, which is 100 minus 8 pi, which equals whatever it is. Okay? So the key thing with our modelling sort of scenarios here is to come up with these two equations. Cylindrical tin gives me that formula there for the volume, and it gives me this formula here for the surface area. Okay, and I'm going to need both of them because I can't work out a derivative if I have two different variables. All right, see how you go. Actually, yeah, see how you go.